Third part, induction voltage and current within a moving magnetic and stationary coil. Faraday law of induction states that a changing magnetic field will induce an electromotive force in a loop wire. The electromotive force causes electrons to move and form a current, changing the area of loop of wire and changing the angle between the loop and the magnetic field can both induce a current. This is because of the property that directionally induced EMF non-electromagnetic measure the total magnetic field that runs through a loop of wire when its field change. Electromagnetic force. So here is the diagram. S is the south pole of magnet and it is indicated by blue color, and is negative pole and north pole, and direction of movement galvanometer. So we can use a magnet and a coil of wire to generate an electric current. In the illustration above, moving the magnet in and out of a stationary coil of wire will induce a current into the coil, and it is due to physical movement of magnetic flux. The faster the movement of the magnet, the greater the amount of current produced. When the magnet is stationary, there will be no current in the coil. It is the same with the stationary magnet and moving coil. If we move the coil of wire back and forth within the stationary magnet, electric current will be induced in the coil. So this is all about coil. So now what is the purpose of coil clearing? So in this link I will discuss so this is not helpful for us. We back this and we will search another what you should know about coil unplug ignition. So now is what is inductor. An inductor, also called a coil choke or reactor, is a passive to terminal electric component that stores energy in a magnetic field. When electric current flow, an inductor typically consists of an isolated wire wound into a coil. Inductor. So we going to be back from this because this is not so we learned from electronics tutorial. We learned from basic factor. The inductor is a passive electrical component consisting of a coil of wire which is designed to take advantage of a relationship between magnetism and electricity as a result of an electric current through the coil. In our We saw that when an electrical current flows through a wire conductor, a magnetic flux is developed around that conductor. This effect produces a relationship between the direction of the magnetic flux, which is circulating around the conductor, of the direction of the current flowing through the same conductor. This results in a relationship between current of magnetic flux direction called Fleming right hand rule. But there is also another important property related to a wound coil that also exists, which is that a secondary voltage is induced into the same coil by the movement of magnetic flux as it opposes the resistance any changing in the electrical current flowing it. In its most basic form, an inductor is nothing more than a coil of wire wound a central core. Inductor also called choke and another passive electrode component consisting of a coil of wire designed to take advantage of the relationship by inducing a magnetic field itself. Core a result of the current flowing through the wire coil. Forming a wire coil into inductors result is a much stronger magnetic field than one produced by simple coil of wire. Inductor also form with wire tightly wrapped around a solid central core which can be either a straight cylindrical rod or a continuous loop or ring to concentrate their magnetic flux. The schematic symbol of an inductor is that of a coil of wire, so therefore a coil of wire can also be called an inductor. Inductor usually are categorized according to the type of inner core. They are wound around, for example, hollow core, free air, solid iron core, or soft ferrite core, with the different core type being distinguished by adding continuous or dotted parallel lines next to the wire coil as shown below. Inductor symbol: air core, iron core. So this is air core inductor and this is iron core. This is the ferrite core inductor and this is variable core. And this is the diagram. L's indicate the length of cylinder, inner core material, cross-sectional area and number of turns V. The current flow through an inductor produces a magnetic flux that is proportional to it. But unlike a capacitor which opposes the change of voltage across their plates, an inductor opposes the rate of change of current flowing through it due to the build-up of self-induced energy within an electric field. In other words, inductor resist or oppose changing of current but will easily pass steady state DC current. This is the opposite change of current but will easily pass a steady state DC current. This ability of an inductor to resist change in current and which also relate current I with its magnetic flux linkage as constant proportional called inductance, which is give a symbol L and its units is Henry after Joseph Henry because the Henry is a relatively large unit of inductance in its own right. Of smaller inductors, sub units of Henry are used to denote its value. For example, millihenry, microhenry, nano. So to display the subunits of Henry, we would use an example 1 millihenry, which is equal to 1000 of Henry. 1 microhenry. Inductor coil are very common in electrical circuit and there are many factors which determine the inductance of coil, such as the shape of coil, the number of turn of insulated wire, the number of layer of wire, the spacing between the turn, the permeability of core material, the size of cross sectional area of core, the name of to name a few. An inductor coil has a central core which is constant number of coil of wire per unit length. So if a coil of n turn is linked by an amount of magnetic flux, then the coil has a flux linkage and any current that flow through the coil will produce an induced magnetic flux in the opposite direction to the flow of current. Then according to Faraday's law, any change in the magnetic flux linkage produces a self-induced voltage in the single coil, where n is the number of turns, a is the cross-sectional area, is the amount of flux in Weber, u is the permeability of the coil material, I is the length of the coil in meters. Change a time varying magnetic field induces a voltage that is proportional to the rate of change of current, producing it with a positive value of indicating an increase in EMF and a negative value indicating the decrease in EMF. The equation relating This self-induced voltage, current, and induction can be found by substituting the micro and 2 with the L denoting the constant of proportionality called inductance of the coil. The relation between the flux in the inductor and the current flowing through the inductor is giving as inductor consists of a coil of conducting wire. Then this then reduce the above equation self-induced, sometimes called the back EMF induced in the coil 2, where L is the self-inductance and the rate of current change. So from this equation we can say that the self-induced EMF equal inductance times the rate of current change, and a current circuit that has inductance of 1 Henry will have an EMF of 1 volt induced in the circuit when the current flowing through the circuit. When the current flowing through the circuit changes at the rate 1 ampere per second, one important point to note about the above equation, it only relates the EMF produced across the inductor to change in current, because if the flow of inductor current is constant and not changing, such as in steady state DC current, then the induced EMF voltage will be zero because of instantaneous rate of current change in zero. With a steady state DC current flowing through the inductor, and therefore zero induced voltage across it, the inductor acts as a short circuit equal to a piece of wire of at a very least a very low value resistance. In other words, the position to the flow of current offered by inductor is very different between AC and DC circuits. The time constant. We now know that the current cannot change instantaneously in an inductor. Because of this to occur, the current would need to change by a finite amount in zero time, which would resulting in the rate of current changing being infinite, making the induced EMF as well, and infinite voltages do not exist. However, if the current flowing through an inductor change very rapidly, such as with the operation of a switch, high voltage can induce across the inductor coil. Consider the circuit of a pure inductor on the right with switch open, no current flow through the inductor coil. As no current flow through the inductor, the rate of change of current in the coil will be zero. If the rate of change of coil is zero, there is no self-induced back EMF within the inductor coil. If we now close the switch, current will flow through the circuit and slowly rise to its maximum value at a rate determined by the inductance of the inductor. This rate of current flowing through the inductor multiplied by the inductor inductance in Henry result in some fixed value self-induced EMF being produced across the coil as determined by the Faraday's equation above. This self